All right, this is lecture 25, talking about relative extrema. We're going to start with an example, information that we did in lecture 24. I have a function f of x equals x plus 1 over x, and I want to know where the critical points are and where it's increasing and where it's decreasing. The first thing I'm going to note is the domain is everything but 0. So negative infinity to 0, union 0 to infinity. So 0 is a discontinuity. All right, to find the critical points and to find where it's increasing or decreasing, I need the derivative. So f prime of x is 1 minus 1 over x squared. To find the critical points, I set this equal to 0, and I get 1 over x squared equals 1. Multiply both sides by x squared. I get 1 equals x squared, and x equals plus or minus 1. All right. Also notice that the derivative is undefined at 0, but it is not a critical point because it's not in the domain. Right now, what we do is we put our critical points and our discontinuities on our number line. So I have -1, 0, 1. And then I plug in a number in each interval into the derivative, because the derivative tells me slope. If it's positive, I know it's increasing. If it's negative, I know it's decreasing. If I plug in -2, I'm going to get something that is positive. If I plug in 1/2, I'm going to get something that is negative. If I plug in positive 1/2, I'm also going to get something negative. I'm going to put this line right here just to indicate that that is an asymptote at 0. And if I plug in something bigger than 1, say 2, then I get something positive. So I'm increasing here, decreasing here, decreasing here, increasing here. So I'm increasing from negative infinity to -1, and from 1 to infinity. I am decreasing from -1 to 0, and from 0 to 1. Okay, so let's sketch this graph. So first of all, like I said, there's a vertical asymptote. At x equals 0. I have critical points at 1 and -1. F of 1 is 2, and f of -1 is -2. I plug that into my original function. So I have the point 1, 2, and I have the point -1, -2. So I'm going to put those points on there. And I have 1, 2, -1, -2. All right, and we said that is increasing to -1 and then decreasing after -1. So it's going to look something like this. And then it is decreasing until +1 and increasing after that. So I have a graph that looks something like this. All right, now we have those two critical points have special names, and we call them relative maximums and relative minimums. If I am in an open interval, so I'm in some interval, say between here and here, if everything around it, a point, is smaller, then we call that a local max. So if f of x is less than or equal to some point c, some y values evaluated at c, then we call that a local max. If everything around it is smaller or bigger, sorry, then I call that a relative min. And I'll show you what those look like. So in our example, I have a relative max here because it is the top point and everything around it is smaller. I have a relative min here. We call these relative extrema. That is the relative max and min. Sometimes it'll say, some books will call it local. All right, so let's take a look at an example. If I'm looking at this graph, I want to find all the points where around it, around that point, if I want to find the relative maximums, around that point, everything on the graph is smaller. So I would say that this is a relative max and this is a relative max. Now for minimums, I want everything around it to be greater. So here is a relative min and here is a relative min. So I have maxes that occur at x equals -1 and x equals 3. And I have minimums that occur at x equals 2 and x equals 4. Now let's look at those particular points. We should notice that those are critical points, right? It's either where there's a horizontal asymptote or where it's not differentiable. So in other words, where f prime of c is equal to 0, or where f prime of c is undefined. And we know those are our critical numbers. All right, now we have kind of a theorem. It's called the first derivative test. And this is a test so that I know that it looks like this is a test to decide if it's a relative max or a relative min without having to look at the graph. So if my y value evaluated at C is a relative maximum, so here's my point C, if I'm increasing on this side and decreasing on this side, then I have a relative max. So if I switch from increasing to decreasing, I have a relative max, because that's going to look something like this or something like this. This, if it has a horizontal asymptote, this, if it's not differentiable at that point. Now, if I switch from decreasing to increasing, then I have a relative min. And that's going to look something like this or something like this. If it doesn't change signs, if it doesn't go from, if it's increasing and then increasing, or decreasing and decreasing, then there's no relative max or min. All right, so let's do an example, and we're going to find all the extreme values, the relative extrema. So here's a polynomial. F of x equals 2/3 x cubed minus x squared minus 12x plus 4. The first thing I'm going to note is the domain. It's a polynomial, so I know that the domain is all real numbers, so from -infinity to infinity. Now I want to find my critical numbers, and I know I find my critical numbers by taking the derivative and setting it equal to 0, or finding where the derivative is undefined. I get 3 times 2/3 x squared minus 2x minus 12. So I set that equal to 0. My 3's cancel. I get a 2x squared minus 2x minus 12. I'm going to factor out a 2. And that gives me an x squared minus x minus 6, and that factors as x minus 3, x plus 2. So my critical numbers are at x equals 3 and negative 2. All right, now I'm going to put those critical numbers on my number line. See where it's increasing and decreasing. So if I plug in something less than negative 2, say negative 3, I'm going to have a negative times a negative, which is positive. So it's increasing on that interval. Between negative 2 and 3, let's choose 0. That's going to give me something negative times something positive. So that is negative, which means on that interval, it's decreasing. And then something larger than 4 or larger than 3, let's say 4, I get something positive times something positive, which is increasing. All right, so I know it switches from increasing to decreasing at negative 2. So there's a max here, and it switches from decreasing to increasing at 3. So there's a min there. We want to do just a rough sketch of this. So I need to find the critical points, right? So I have the critical numbers. I want to figure out what the critical points are. We just said that the max occurs at x equals negative 2, and f of negative 2 is 18 2/3. So the max is 18 2/3. The min occurs at x equals 3. Whoops, that was a negative 2, sorry. And f of 3 is negative 23. So I'm going to plot those 2 points, negative 2, and I'm just going to do a rough sketch here. And then 3, negative 23. And then I'm going to go ahead and put my y-intercept, because that can be found easily. Just plug in 0 and I get 4. So right here. And from our number line, we know it's increasing up until it's max, decreasing until it's min, and so on. All right, so it looks something like this. All right, next question. Find all critical points and intervals on which the function f of x equals x cubed minus 3x squared plus 3x is increasing, decreasing, and find relative extrema. So this is the same type of question. The domain, again, is negative infinity to infinity because it is a polynomial. I'm going to take the derivative because that's going to tell me where my critical numbers are. I get a 3x squared minus 6x plus 3. I set that equal to 0. I'm going to factor out a 3, and I get an x squared minus 2x plus 1. And I factor that as x minus 1 times x minus 1. So my critical number is x equals 1. All right, if I plug in something negative, we'll notice that I can rewrite this as 3 times x minus 1 squared. And something squared is always positive, right? So I'm going to be increasing everywhere because there's not a number that I can plug in and get something negative. So I'm increasing from negative infinity to 1 and from 1 to infinity. Since it is increasing and then increasing, it doesn't change from increasing to decreasing or decreasing to increasing. There are no extrema. There's no local max and there's no local min. All right, let's try one more example. Given f of x equals x to the 2/3 over x minus 1, and they give us our derivative, which is f prime of x equals negative x plus 2, 3x to the 1 over 3x to the 1/3 over x minus 1. So I'm going to note the domain. and it's going to be every number except for 1. There is a vertical asymptote at x equals 1. Now I want to find my critical numbers. I'm going to set my derivative equal to 0, and they give us the derivative, negative x plus 2 over 3x to the 1/3 x minus 1. Now let's notice that the derivative is undefined at 0 and at 1, right? 1 is not a critical number because it's not in the domain, but x equals 0 is a critical number because it's undefined. All right, now if I multiply both sides by the common denominator, I get 0 equals negative x minus 2. So I get x equals negative 2. So my other critical point is x equals negative 2. Now, when we put this on our number line, remember that we also include our discontinuities. So I'm going to include 1 as well. So I have a negative 2. I have 1. Wait a minute, I have 0 and I have 1. And remember, 1 is an asymptote. So I'm going to put something that looks like this. All right. Now, if I plug in something negative, say negative 3, I'm going to get something positive in the top, and I'm going to get something negative in the bottom. So I'm going to be decreasing on that interval. If I plug in something between 0 and negative 1, then I'm going to get something that's positive. If I plug in something less than 1 but greater than 0, I'm going to get something negative. And if I plug in something bigger than 1, I'm also going to get something negative. All right, so it switches from decreasing to increasing at negative 2, so there's a min there. And it switches from increasing to decreasing at 0, so there's a max there. Now notice it doesn't change at 1, but even if it did, since there's an asymptote, it couldn't be a max or a min. All right, so I have a min that occurs at x equals negative 2 and a max that occurs at x equals 0. All right, and one application problem, the demand and cost function for per new product at a fast food restaurant has been determined to be P of x equals 3.2 minus x over 20,000, and the cost equal to 0.76 x plus 4,800, where x is the number of items sold per week, somewhere between 0 and 35,000. For what sales level will profit increase? What price should be charged to maximize profit? All right, so what I need to do is I need to maximize my profit function. I don't have a profit function, but I can come up with a profit function. Remember, profit equals revenue minus cost. And the revenue function is the number of items sold times the price per item, and then minus our cost function. All right, so x times P of x, 3.2 minus x over 20,000 minus my cost function, 0.76 x plus 4,800. Let's add let's go ahead and distribute the 3.2 so that I get a 3, or the x, so I get a 3.2x minus 1 over 20,000 x squared minus 0.7. I'm distributing the negative sign, so I get a negative 0.76x minus 4,800. And now let's add like terms. And I get a 2.44x minus 1 over 20,000 x squared minus 4,800. All right, so now I have a profit function. I know the maximum, to maximize this profit function, I need to find the derivative to see if it changes from increasing to decreasing. So I'm going to take the derivative of my profit function. I get 2.44 minus 2 over 10,000 or 20,000 x. I'm kind of out of space, so I'm going to erase this here. I'm going to set this equal to 0 and find the critical number. So 0 equals 2.44 minus 2 over 20,000 is 1 over 10,000 x. So 1 over 10,000 equals x equals 2.44. Multiply both sides by 10,000 and I get 24,400. All right, then the last question says, what price should be charged? And to do that, we need to plug 24,000 into my price function. So 24,400 into my price function, 3.2 minus 24,400 over 20,000. And we plug that into our calculator and see what we get. We get 3.2 minus 24,400 divided by 20,000. All right, so it looks like $1.98. All right, that's it. Please go ahead and watch the introduction to lecture 26 as well. Have a good day.